Hey everybody, it's Florian Musso again. As most of you will know, I'm an architect and not an engineer. So you might ask yourself, why am I talking about structures that much if I'm an architect? Basic understanding of engineering issues for architects is a necessity to be capable to discuss with engineers about architecturally relevant parts of the load-bearing structure. So one of these elements is the horizontal structure. We've been talking about beams before, and that inside the beam you would have the upper part being charged in compression and the lower part being charged in tension, and there's a neutral zone in the middle where this changes. So now I could go and put different beams one next to the other, and this would give me a sort of plate. But basically there would be compression in the upper part and tension in the lower. And I could also go ahead and cut the beam in half and put the section in a more favorable position, and then I would have to link these two by a sort of weave or diagonals, and this would be called a truss then. So the truss has two parts, the upper part being charged in compression and the lower part being charged in tension, and then we have to link both of them, for example, by diagonals, and so that the compression part and the tension part would work together and not alone as beams, as we have seen before. So these diagonals could be buckling, and to avoid this buckling effort, we could try to have the diagonals that are charged in compression to make them shorter, and to make those that are charged in tension longer. So if I have a truss, and this truss would be linked by diagonals, which is one form of the truss. We also have the truss with rigid angles. This would be called a Vierendeel truss. So I want to find out which one of these diagonals are charged in compression and which ones are charged in tension. So if we have our systems, and I want to know how this diagonal here is solicited, I could take this as being stable, and what would happen then? This would stay stable, and this one here would transform into a parallelogram. And this parallelogram would mean this is getting longer, so that means tension. This is getting shorter, this would be compression. So if I have a material where the linkage can be done easily, I would try to put the diagonal in tension, as the danger of buckling is lower than in the other case. So for a steel truss, this would mean that the diagonals should be falling to the middle, and so that they would always be charged in tension. Upper part being in compression, the lower part being in tension, and the diagonals, as we have seen here, would then be charged in tension as well, so I can make thinner. For example, with a narrower rod or with a cable, than the other way around. Although you can see in older wood trusses that the linkage here was not that easy at the time, so sometimes in wooden trusses the diagonals are the other way around. So unfortunately this wonderful bridge structure that my students did here is broken, and you can see though in how far the diagonals work together with the upper and the lower chord, and where I take the diagonals out because the connection is harmed here, the geometry of the truss starts to move and it becomes fragile. So some of you might have heard of the Spanish architect, engineer Antoni Gaudí. And Gaudí has been experimenting with optimum forms. He used chain models as to determine the most effective forms for his buildings. So if I suspend a chain here, I'm going to try to make it hold. Yeah, it holds. You can see that from this point of suspension to this point of suspension, it describes a sort of parabola. And there's also a horizontal part here in the system. You will see this when I push it out. It will try to get back into the original form, which is due to friction here on the upper part. The more horizontal I make it, the bigger this horizontal load here becomes. And if I translate this to a beam, I could see that the beam has a moment diagram as well, which is maximum in the middle and it becomes zero at the end. And I could use this to optimize the form of the beam in the way that this could be the lower part and this could be the upper part, and the beam becomes something that looks like a fish belly. Where I want to have a big span, like for example the Verrazzano Narrows Bridge, I can push these suspension points here up by columns and then try to get the horizontal load into the ground, and then I could be spanning over a river or so and drive somewhere in the middle. And as to link the driveway to the suspension, I could do this with another set of cables. If I have a different situation, like for example in the Alps, so I have a valley and I want to get from one side of the valley to the other, I could use an arch structure as well, which is a little bit the inverse of what we have seen before. So here I have a lot of space below, could place an arch. The arch would be, the ideal form would be the one that we have seen in our suspension experiment before. And then I could link this arch structure to the driveway and get some sort of horizontal load-bearing structure as well. So this thing spans from one point to the other, and if I'm introducing another support, you can see how I cut the whole thing in half, or I would be able to double the span.